All right, so we can cover all the reactions that'll do this. So if you have a primary alcohol and you want a aldehyde, yeah, you're gonna need to do a swern. Oops, which would be what's that? COCl2, um, DMSO, and triethylamine in several steps, right? And so that's one way to do it. You can do absolutely the PCC, which is what chromium and pyridine and HCl, if I remember correctly, and DMP, of course. And what else will do this? Those are our like kind of gentle ways, right? All of these will also work for ketones, right? All of those will work for ketones. Plus, you can use permanganate. You can use the dichromate. You can use chromic acid, Jones, right? So you've got all sorts of fun stuff that you can do. So swern oxidation, pyridinium chlorochromate, Des-Martin periodinane, and then what else do we have? Potassium permanganate, dichromate, chromic acid, those sorts of things. So yeah, all sorts of fun oxidation. DMP is Des-Martin periodinane. Is periodinane. Periodinone? Ooh, I don't remember. But yes, here. I'm gonna Google it real quick because I think I'm spelling that wrong. Um, is DMP something you've covered in organic? Because I know it's a relatively newer reagent, and I don't know if oh, I did get it right. Pyridinane. Yeah, it is an A. Okay, I was right. Um, as a mild oxidizing agent, fairly recent, last couple of decades. So I don't know if Travis and Oganessian teach it, but yeah, that'll it's a great way to oxidize gently. So because remember, if you use any of these kind of secondary ones on a primary alcohol, you get the carboxylic acid. So because they are more aggressive oxidizing agents. Hmm. So there's those. I think Carlina, you had asked. You do not need to put Dean Stark everywhere. Mrs. O likes to do that. She likes to talk about lab kind of realism in the lecture. It's not necessary. So, yep. We vaguely went over it, but it's not something that's super important. So, yeah, it's a lab technique. Hmm. Go ahead. Yep, correct. Okay. Uh-huh. So what you want to do is that means you're going to need a blocking agent. So if you're going from, this is terribly ugly, but let's say you have, if you're trying to do something like this, something like that, where your primary product is ortho, what you first have to do is, yeah, yeah, yeah. So I would definitely do that if that's the case. So there's technically some distinctions you can probably make. You can be like, well, OME is probably a small enough group that the ortho is not sterically hindered, but You know, it's kind of a just safer bet to just do para. Or if you wanted on ortho to, yeah, block off the para position. So, yeah. Well, you'd have to prevent it from doing that. So I would always do it this way. Do this way and then do your Cl2, AlCl3 or iron, and then you'll get the product with the sulfonate, and then you just dilute sulfuric acid, and then now that way you guarantee it, right? Because yes, if you just throw the chlorine on, you'll get a mixture of products, some para, some ortho, right? And so if you want to guarantee it, then yeah, you'll have to block it off. Mm-hmm. Yeah. Okay. All right. Let's see here. Si4. Okay. Is that the one that's like labeled Si4? Because okay, I know because she has Si4 as like, or the key for that as, yeah. All right. Why is this not displaying? Okay, hold up. Okay. Which number are we looking at? Indeed. Okay. All right. Let me just take a look here real quick. Okay, so it's just a Friedel Crafts we're doing. Yes. Oh, and then she's got some. Oh, yeah, because remember that with Friedel Crafts, when the carbocation you make is not ideal, it will migrate, right? So, yeah, let's talk about it. Yeah. So, what? Tell me your process. Okay. Like, what else would you get? It's yeah. Mhm. Mhm. Well, so the bromine is originally on the methyl, right? So when it leaves, the carbocation is on the methyl group. So she's drawn the. Let me draw it a little bigger because I think it's super small what she's drawn here. So, uh, let's see. All right, let me draw it real quick and then I'll switch. Uh, Actually, you guys can see it right now, but I'll switch it for the people who are watching the recording. So we have. Boop, 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 boop. I think 4 carbons there, and then Br. Okay, cool. So we have this thing. So it goes away. Carbocation, right? Carbocation will migrate, and we're going to end up with exactly the same thing. Now our carbocation is there in the middle, and then our benzene comes in. I guess I need to draw them out. And it's going to come in and it's going to go ahead and attack that position. So we're going to end up with a butyl group, what propyl group, and a methyl group on this benzene, right? After we do all the other stuff. So at the end of the reaction, you're going to end up with your benzene. You're going to have a methyl group, a propyl group, and a butyl group in whatever stereochemistry, because it's going to be racemic. So it doesn't really matter which one you get, but that's what I would do. Um, Oh yeah, I mean just rotating and stuff. So yeah. No, yeah. I could totally have done this. I could say now my methyl group is over there, and this is now my butyl group. Like no problem. So as long as the numbers of carbons are correct, you're good. Awesome. Cool. Si6, huh? Okay. All right. Go ahead. I will pop it open. Mm-hmm. Uh-huh. Correct. It's just a Lewis acid. It's there to help the process go along. So remember, you can use an acid catalyzed process. It's just a Lewis acid. So yep. You'll end up with tetramethyl cyclohexane. Yep, that's it. Mm-hmm. Methyl cyclohexane, and well, hold up here. Then we've got butyl lithium coming in. So using butyl lithium here. So we're protecting it, and then we're gonna. So the butyl lithium is gonna. I think this particular one might be out of the purview of the class because right, you protect your aldehyde with the sulfurs. Um, and I wonder if she's wanting us to do some sort of alpha proton abstraction thing going on here, an enolate reaction, having us attack this alkyl halide. Uh, I don't think this is something we would cover at this point in the class. We're going to cover that later on. Yep, cool. Okay, put this one back. All right, what's next? Of course not. It's not Sunday afternoon. Are you kidding me? Of course. I mean, it takes hours to make an exam. Like, this is not something that I can just do. No, that's something I usually do the day before or maybe Saturday if I'm feeling extra productive, but probably not. Sure. Dean Stark, remember, is the I'm using the wrong tablet here, but that's the one that it's just the apparatus that helps take water out of your reaction to help push the equilibrium forward. That's all it does. So remember, that's the thing that kind of looks like where you have a little drippy part you can put. So your solvent, as it's refluxing, goes up here, condenses, comes down here, and you're able to get rid of it. So you can take any of the water that was also refluxing out. Um, it just removes the water. So it pushes your equilibrium forward. Because remember that if you're doing some sort of, whatever, thing like this, it's an equilibrium reaction, right? 7 steps or whatever, however many it is. So we're just using the process of Le Chatelier's principle to remove the water. So a Dean Stark apparatus removes this dude. And that's one way to do it. So you can put molecular sieves in there also. You can use a Dean Stark apparatus. You can use a solvent that doesn't mix well with water. like toluene or something. And so you just have other ways to get rid of it. So it's something that's lab related. Mrs. O likes to put that on all of hers. And I think it's just a little bit unnecessary. So it's extra information. hmm So just an extra step to get rid of water.
It's not necessary.
No, no, not on paper. I mean, you can do you can use Dean Stark for making esters as well, but I mean, did you guys do the like fake banana oil lab
No.
last semester? Okay. Oh, it's for this semester or for? Oh, it was canceled last semester. Okay. Well, had you done it, you would see that you just do it as a plain old condensing in a regular old condenser, nothing special. So you don't even use a Dean Stark in the lab for making the ester, but notice, lo and behold, making an ester, you've got your carboxylic acid plus your alcohol. It's exactly the same idea. Also produce water, and I have used a Dean Stark apparatus when doing esterification reactions, but they work just fine without them. So um, it's somewhat unnecessary. So technically, you can use a Dean Stark whenever you are producing water as a product for an equilibrium reaction, which most organic reactions are, but again, not really necessary. So. All right, what else would you like to go over? I eat this croissant in the meantime.
The whole point
Like ether? No, you're making a double bond. Oh, how dare you make me stop eating? Okay, so let's take this thing. And look, we'll even make it an aldehyde for once. Horner Wadsworth Emmons. What do we want to put on this? I don't know, methyl, and then no, other side. So this I could draw as a double bond, right? Uh, that is the double bond to phosphorus. There, does that make it better? So, yes, yes, yes. So what happens here? You will end up. Oops. Oh my God! Look at all these colors. Okay, no. No, go away. Oh my God. All right. You're gonna end up condensing this too, right? So you can keep the top part, or keep everything but the O, and you'll just put in the rest. And since this is a stabilized one, we're gonna get our bulkier groups on opposite sides. So our T-butyl goes here, our ester goes there, and poof, we're done. So we're making a double bond to carbon. That's what we're making with a Horner Wadsworth Emmons type thing. It's the same thing as Wittig, yeah. It just uses this. That's the only difference. So stabilized Wittig, special case. But notice you get the transalkene, as it were. One is stabilized. And the unstabilized one would be the opposite. Correct. So if you were to just do like that, yeah, you're going to get them on the same side. So that's the difference. It just read geochemistry. Notice I could even put this, if it's too far away, can't resonate, doesn't stabilize it. Got to be right next to it so it can stabilize the negative charge. Remember, because this is really plus minus. If the ester is too far away, or your electron withdrawing group is too far away, it's not stabilizing your negative charge. So lots of things to keep in mind. No. Yes, because it's right next to it. So if we can resonate if we want to. Too far, no resonance. You can't resonate this way. If you do, you end up with a carbon with 5 bonds, which is height illegal. Yes. Or like if you have it the opposite way too, even if you have something like this. This is not stabilized either. This is the opposite of stabilized. Because this one pushes electron density. Like this thing is not an electron withdrawing group, it's an electron donating group, right? Because we have the oxygen here now. We in fact are pushing electrons towards our thing. So that's an electron donating group. It has to be the carbonyl side of the ester. Lots to think about. I'll draw the opposite one just so we can see. The same group, but flipped around. Now it's stabilized. Mm-hmm. Yeah. Mm-hmm. Look at that. Yes. Well, a nitrile would stabilize, right? But without the nitrile, it's destabilized. The nitrile by itself is certainly an electron withdrawing group, so you can totally resonate this thing. So, yeah, this is also stabilized. Mm-hmm. which again we will call not Z. But yes. All right. What else would y'all like to go over? So he canceled lab again. Oh, that's kind of hilarious. I know that's kind of messed up, isn't it? No lab, but you still get a quiz. Yay. Mm-hmm. Not something we've covered yet. Eyeball H. So that turns this into an aldehyde, but that's something we haven't covered yet. So that's part of when we talk about nitriles. That's diisobutyl aluminum. That's definitely a capital L then. So that's the reagent that you would use for this, but yeah, not something we've covered yet. So don't worry about it. We will talk about that next chapter. Mm-hmm. I don't know yet. Haven't written it, but it will be same format at least. So I don't know. Sorry, but yeah, I'm not quite sure how I will frame the mechanism, but I will be very specific about what I want you to do. So if there's multiple products or something that I'm showing you, or I'm asking you to show these products, I'll be very clear. Or if I'm doing an EAS or something, and I want you to show the sigma complex resonance, I will say that. Or as you are always so afraid of the Meisenheimer complex for an NAS reaction. Of course not. It could be the only question on your exam. So, yep. Cool. What's next? Naming problems. Those are easy to make up. Here we go. Let's do it. Easy comp. Indeed. So this will be best named. I mean, you could name this two ways, right? You could name it as a substituted benzene, but why? That would just be way too much work. But I would say, yeah, it's probably easier to just name this as a butanal for sure. All right, of course, and we'll go this direction because we have more substituents that way. What do we got? Fluoron, indeed. Fluoron. Very good. Ah, there. Oh, I see. Now that makes a little more sense. Yes, we have. Well, remember that we're going to call it a fluoro group. No, you didn't. You said fluoron. Unless you said fluoroon, which then I would. Anyways, what else we got? And the name of that group? Okay. What are we missing? The phenyl. Okay. What else are we missing? No. Toluene would be this dude. Toluene is methylbenzene. This is just a phenyl group. That's it. Isopropyl too. Cool. What are we missing still? The oxygen. Indeed. Not regio. Got it. Yep. Nope. Yep. Stereochemistry, perhaps. You said regio. 1, 2, 3. Boom. This is R. 1, 2, 3. This one's also R. Yay. Don't forget your stereochemistry. Do we see how all those priorities are given? One on the left is the fourth, yeah. Yes. Wait, that's totally an S over there. Why am I saying that's totally S? Going this way, going that way. Looking at them, I'm like, they're going the opposite direction. Why are they the same? It's because I don't know how to do counterclockwise. So, sorry, that's totally S. Yes, and then we just name it. So, we would say 2S or R. Now let's do this alphabetically. Fluoros first, then isopropyl, then so phenolbutanol. No, not IUPAC rules. Might be some common things about that, but nope. They are different functional groups. They have different names. Can we give you all? I mean, there wasn't really naming for the first chapter, was there? Because they're just aromatic reactions. So, not so much there we can do. So naming won't be as big of a portion. Since last time we had uh, a lot of naming. This time we only have one chapter with naming, so won't be too many problems on this. Mm-hmm. Click. Oh, you mean this dude? Yes. Dude. If you're just using it as a protecting group, no, does not matter. However, it is usually better to use a cyclic one. The reason being, if you have multiple carbonyls, the cyclic one can only attack one of them. If you just throw in methanol, it's hard to say that you're going to get. I mean, eventually, yes, you'll only get the aldehyde one protected, but harder to make that statement, right? So just cyclic ones in general. So I mean, if it's the oxygen-based one, ethylene glycol, or if the sulfur one, doesn't matter. Those two would be equivalently good. Oops. Either of those would be good choices to protect something. Okay. Mm-hmm. Yep. HCl and KCN. Just H plus. Yeah, yeah. So, because if you just put KCN with HCl, that totally works. Because what's going to happen is your CN is going to go grab a hydrogen, and now you have HCN. Ta-da! Yeah, so that works too. Mm-hmm. For sure. So you can use KCN HCl. You can use KCN HCN. HCN, of course, is very, very toxic. It is the cyanide that people die to. So, yes, I can understand the reason to not want to use it as a reagent directly. We don't typically carry cyanides, but yes, theoretically. We have acetonitrile, so, but that's not something that's acidic. So, well, it kind of is, but not acidic in that way. So, it can form not enolates, but similar things. But that's neither here nor there. So either of these sets of reagents will work. Yeah, for sure. We use NaCN as well. Go right ahead. Sodium instead of potassium. Not a big difference.
I don't really have any other questions.
Cool.
There was a lab.
Might as well. Okay. All right, anyone else have anything they'd like to go over? Nope, unfortunately. When I was stealing stuff off her website, those two came together as a pair, as like the SI and the key, and I'm looking at them. I'm like, one is labeled 5, the other's labeled 4. They have the same kind of content, but they are not the same questions. So, um, worst case, what I suggest you do, put them in our Discord general chat here if you have questions on them, because I've looked at some of your classmates who've been like, can you just take a look at these, and we went through a bunch of them, and so yeah, I'm happy to do that here, or you guys can help each other out. So you're welcome to do that. So, yeah, well, let's do it. Right. So are we looking at like Si5 aldehydes and ketones key or Si6 aldehydes and ketones? The first one. Okay, cool. Yeah. And I noticed the same thing for the aromatics. I was like, really? Like, come on. Okay. Yes, open it. Why? This computer sucks a bit. Okay, so at the end here. So which ones are we looking at? All right. Ooh, it's an enamine. Okay. Okay, yeah, we can do that. So, we have it's just an enamine synthesis, so it's not as bad as it seems. Though her key doesn't have, oh, there is a nitrogen containing compound. Okay, it's like there's no nitrogens in her key. Like, how do you get this? So, enamines, remember, are going to form from, sorry, let's go ahead and, so she's put on the alkyl group first and then done the enamine. So do you want to do it this way and kind of see how it goes? Or um, with this one, the enamine that you choose, if, no, we'll leave it at that. So yeah, you have to do it this way. Okay, so I didn't copy them and I just switched windows. Okay, so we're going from this thing to two cyclopentyl groups. Good to die? No, we're good. All right, so this is what we're looking at, right? Okay. Oh, it totally did disconnect, didn't it? Okay. Yeah, the tablet has decided to do that. Here we go. Should be back in just a sec. There we go. Okay. Yes, this one. So let's take a look at this. We have an enamine here, right? So synthetically, we're looking at for having an enamine, that comes from putting a secondary amine plus a carbonyl, either an aldehyde or a ketone, right? So that's how we make enamines. So if we want to think about how this enamine came to be, well, we can see our secondary amine is going to just be this dude, right? It's already secondary. It's got two carbons on it. That's going to be our amine component. And so the rest of the molecule has to be a ketone, right? So we have to have a ketone for that. So how do we know that? Because remember, enamines, they form the double bond one space away from where the nitrogen is. Remember, amines will form it directly on, but enamines, it's one carbon away. Because it's cyclopentane on both sides, there's no reason to go on one direction or another, but in this case, it's on the right, so it doesn't really matter. But do we see how those two are going to be what makes the product? Good. So we just have to think now, how are we going to get this ketone? Well, if we look at our starting material, we have only one cyclopentane unit, so we need another one at some point on here, right? So we know how to put carbon-containing units on, right? We can say, okay, well, what if we had this thing and say, I guess I need to put that opposite way. Too many carbons. 1, 2, 3, 4. We could use a Grignard reagent on this thing, right? If we use a Grignard reagent and an aldehyde, well, that'll get us to the alcohol, right? Version. This will get us to an alcohol, but it will have our cyclopentanes. If I can draw a cyclopentane. this is what we'll have when we put those together, right? So we just need to oxidize it. What's our favorite oxidizing agent? What do we want to use? PCC. Sounds good. Okay. PCC will get us from the alcohol to the ketone. Ketone with the amine will get us to the enamine. So if we want to think about what we can do with this other thing, with this oxygen to aldehyde, well, that's also just PCC, right? And poof, we've done it. So it's all about taking a step backwards, seeing the functional groups present in your final molecule, as well as what other carbons have been added. So we see in our final product it's an enamine. We have to think, how the heck do we make enamines? Well, we make them from secondary amines and carbonyls condensing together, right? And so then we have to separate it. We have to say, okay, well, the enamine, remember, it really at some point was like this before the base came along, right? So that may be easier for us to see that that's where that's where we're breaking this to figure out the products or the reactants, I guess in this case. So that's how we're going to see we have the cyclopentylamine. 1, 2, 3, 4, 5. Yeah, cyclopentylamine, which looks like a cyclohexane. And of course, we know that it came from a carbonyl. And so we know that that's the ketone. How do we make ketones? Generally from alcohols. Although, again, there's many weird things you could do here. Alcohol's the easiest one because we can go since we needed to add that cyclopentyl carbon unit, we can use a Grignard or a Gilman. Nope, we have not learned Gilman reagents yet, so never mind. But that'll work here. So we'll go ahead and use our Grignard reagent to on an aldehyde to make that alcohol that then we can turn into the ketone that then we can condense with the amine. So it's lots of stuff to think about here. So those are kind of the steps that we go through in this process. So identify your functional groups. Think, how the heck do I make those functional groups? What other carbons have I added on here? How do I add those carbons on? And then just kind of piece things together. So it's the toughest part, right? So ta-da! Enamine. This is a here's a second. This is a secondary amine, right? This is a carbonyl compound. You'd add the amine and some acid. So yeah. Ta-da! Yeah. So it's just that an enamine has to be made from a secondary amine and a carbonyl. That's what it's made from. So that's why we know which amine we need and which carbonyl we need. We break those apart right at that squiggly line. And so we say, well, that's where the amine part comes from, and the other half of the molecule is the carbonyl part. So, and if it were not a nitrogen instead, if it were a carbon, then that means we used a Wittig reagent instead. We would still see that, this double bond part is where we have made the change. So if this was a nothing at all, no. If it were a whatever, cyclopentane, whatever, we would have to have used a Wittig reagent instead. Right, so it is looking at what new bonds are made in our molecules, what functionality we have there. So, but I'll keep this the way it is. That's totally not the right number of carbons now, though. Alrighty. Well, we are out of time pretty much. I have another review to do at 10 o'clock, so we got time for one last question maybe, or just general questions. Same as last time. If you found that one easy, then yes, sure. Only 2 chapters, though. Easier than theoretically last time, which was 3 chapters, right? So, I don't remember. Maybe? It might be 3, because I think your book keeps carboxylic acids and carboxylic acid derivatives as 2 separate chapters, whereas mine puts those 2 together. So, for me, it's 2 chapters. For you guys, it's 3. Maybe. If I remember correctly. So, we'll get there later. Alrighty. Of course. Yes. Yes, I shall. All right. Very good then. Take care, guys.